right, well, hello everyone. I'm Jeremy. I'm from the Waterloo office on the bindings team, and I'm here to talk to you a little bit about Speedometer. So first, just an introduction of who we are. The Blink bindings team at Google is primarily located in two sites, Waterloo in Canada. So there's me, Lucas, and Aditya at that office. And here in Tokyo, Bashi, Harakin, Peria, Yukishino, and two interns, Lisa and Sayaka. They're focused on interoperability and our implementation of the WebIDL standard. We also work closely with folks from other teams. That includes the V8 team, principally, but not only in Munich, the rest of platform architecture. And we also accept contributions from a number of valued external contributors. We're also not the only part of the Chrome team working on Speedometer. For example, there are folks in DevRel working on making the Speedometer benchmark itself better. And there are folks in V8 working on making the VM and runtime performance better for Speedometer as well. So what is Speedometer anyways? So Speedometer is one of a long series of browser scripting benchmarks released over the last decade or so. Some of these benchmarks, like Dremio, have been micro benchmarks of a particular aspect of the browser. In the case of Dremio, that's DOM performance. Others, like Jetstream, have concentrated on computation-intensive JavaScript applications with test cases including data compression, Navier-Stokes solving, etc. Today we're interested in Speedometer, which is this one here. So Speedometer is originally released in 2014. You can see Apple's nice WebKit blog post about it. And it's intended to be a benchmark of realistic web applications. And that's at web applications which actually use the DOM and don't just do pure computation. So Speedometer automates interactions with a simple to-do list application from the to-do MVC set. It simulates user interactions using the script APIs like HTML element click and setting the value property of input elements. There's a version of the to-do app implemented in vanilla JavaScript. And then there's also versions implemented in 6 different popular frameworks. So that's React, Backbone, jQuery, Ember, Flight, and Angular. And this is meant to simulate the typical use of JavaScript code manipulating the DOM in real-world applications. So each framework in Speedometer is broken into a number of steps for the test case. A step might be something like fill in this text field and hit enter, and then repeat that 100 times. Each step does some synchronous work, so it'll synchronously dispatch some events. Those events will cause script to run. That script will manipulate the DOM, and that might possibly cause synchronous style or layout. And then when that's done, it uses set timeout to wait until asynchronously scheduled tasks run. This is intended to capture a single run of the rendering pipeline, so this allows layout to run, style to run, well, the other order, paint, compositing possibly. And then when that timer fires, the measurement period ends, and the next test step is scheduled. Speedometer uses real-world frameworks with a synthetic but realistic application, the to-do application, and it drives it in an automated way. You'll note that the example I gave, which is a real example of filling in 100 to-do items, is a little bit more than a user might be able to do within a single frame. But it attempts to strike a balance between simulating the real world accurately and being a consistent, easily automated benchmark. Being bindings folk, we're concentrated for the time being on the synchronous part of this, but the Speedometer score also captures the asynchronous time on the right. Both of these are measured using the performance now timer that's exposed to web apps. Then there's a score that's computed. The Speedometer score is the number of runs of the entire test suite, which could be completed per minute. So that makes it inversely related to the arithmetic mean. This does, however, mean that slower versions of the application are weighed more heavily in the overall Speedometer score. So if, for instance, the Ember version of the 2D MVC app is slower, a 2x improvement to that will have a larger impact on the Speedometer score than a 2x improvement on one of the other frameworks. A second version of the Speedometer benchmark is under development, collaboration between Chromium and WebKit folks and so on. And it takes a similar approach to Speedometer 1.0, but it broadens the framework coverage, and it switches to using a geometric mean to average the time for different tests. And this means that it will weigh proportional changes in the performance of tests equally. I'm told Speedometer 2.0 will be ready by the end of the month, but for the time being, we are still looking at Speedometer 1.0. At the end of the run, the Speedometer UI gives you a nice screen like this. It's got a speedometer graphic on it, so you know whether you're fast. I guess you're really fast if you're in the red zone. And this is on my Chromebook Pixel, which got about 100 runs per minute. So how are we doing on Speedometer? So here's this, just to be confusing, I've decided to show here time to complete the benchmark, which is inverse of the speedometer score. So whereas normally higher is better on speedometer score, here lower is better. So here's how we compare it to some other browsers on the Mac. This is data collected by Lucas on a MacBook Pro. And you can see here there's some opportunity to improve our performance a little bit. We can break that down by the individual tests. And you'll notice the performance actually varies quite a bit depending on which framework implementation you're looking at. Ember, which I gave an example, takes considerably longer to run than, say, Vanilla.js. And that's true across browser implementations. We're paying attention not only to the tests which are particularly slow in Chromium, but also those where another implementation has a significant edge on us, because that might suggest that there's opportunity there to optimize. So where are we spending our time? Why are those taking so long? Well, I'm going to get to that. So nested BlinkOn docs. Just going to play this now. No. So last year, you may have seen a talk at BlinkOn 6 given by Camilo and Tone from the V8 team, talking about V8's approach to real-world benchmarks. The data they collected was from something that V8 has called runtime call stats. And one of the things that you might have noticed if you look closely at those fancy graphs that are behind there is that a large part of the time was spent on what V8 calls callbacks. Callbacks is what V8 says when they mean they've called the embedder, which in our case is Blink, is doing something, and they don't really know what we're doing. So in our case, that's executing Blink C++ code. And we'd like to go take that slice and say, OK, well, what actually are we doing inside Blink? So just to go a little bit more in depth about how runtime call stats works, it tracks the total time and the total number of entries into each bucket that it tracks, each counter. And it automatically stops tracking time in one timer when another begins. So this essentially gives us a very high-level view of the top of the call stack over the execution of the script. It's not as detailed as trace events, but it's considerably more lightweight. So to give a bit of an example, you consider this flame chart where there's task A running and task B runs for a little while. It goes back to A and then calls C, which calls D. Runtime call stats only captures what's happening at the top of that stack. So if we extract out the top of that stack, we see we've lost some information here. We no longer know what the nesting is here, but we can see how much work is spent in each slice, in each bucket. And then runtime call stats actually records even less than that. All we're really recording is the total length of time spent in each type of slice and the number of times that we entered it. So this is considerably less context than we normally have from trace events. Why would we do this? This is considerably quicker to record, and this means that we can put these counters in more places in the code than we can afford to put trace events, and still have the code be relatively small and perform well. So back to explaining that Blink C++ slice. To learn more about where the time inside Blink C++ is going, Aditya implemented a Blink version of runtime call stats. So we've landed counters on a number of high-level Blink subsystems, such as layout, on specific bindings code like wrapper object creation, and on the entry points of specific interesting method callbacks. We have a compile time flag to enable a counter on every bindings entry point, but this is off by default because of the binary size and performance impact. You can also add counters yourself using a macros defined in platform bindings runtime call stats.h. And the results can be viewed either using Chrome tracing or duck to a log. We also have tracking on perfbots. Counters are collected in v8.runtime stats.top25, where we collect information about individual counters, and v8 runtime stats browsing desktop, where we collect data only by category. So we collect data at granularity level like parsing or bindings. It's important to keep in mind that Blink runtime call stats, like its v8 counterpart, runs during script execution. This means it does not capture time spent when script is not executing, such as when the rendering pipeline is running in response to the frame timer and not in response to a synchronous request from script. So here's a breakdown of the time spent during script execution in Speedometer. This, again, only includes the time spent during script execution. So you'll see here from where we're sitting, V8 is still a large amount of the time spent. There's still a lot of time spent, running the script and not tweaking the DOM. But there's still a lot of other categories that are us. So a few brief explanations of some of these categories. So here, bindings is specifically specific binding utilities that we use inside Blink to interact with V8. And so this includes things like conversion of large string arguments and wrapper object creation. Callbacks here is every time where we've entered Blink C++ through a bindings method stub, but we haven't attributed it to one of the other buckets. And so this includes work like append child when a script calls no.append child. HTML parsing here includes both the time spent parsing and constructing HTML, and this happens during script as a result of the inner HTML setter. And you can already see from this level of granularity that the frameworks definitely don't look the same. For instance, jQuery spends a lot of time in HTML parsing. And this is because the jQuery to do MVC app updates its UI by constructing an HTML string and then setting it on an element rather than updating existing DOM nodes. You note again that we don't see style and layout a lot here. And this is, again, because runtime call stats captures the time spent during script. And so this doesn't capture the asynchronous part where we're running the rendering pipeline after script is finished. And we can look more closely. We can isolate a particular slice here. So here's the callback slice of the vanilla.js benchmark. And we can look and see exactly what callbacks are being called. So here we can see that for the vanilla.js test, we spend a lot of time in the value setter of HTML input element and the click method of HTML element. And it turns out that these are the methods that Speedometer uses to drive the vanilla.js to do MVC app. You can also see some of the DOM query selector APIs and other things showing up here. On the other hand, if we look at something like Backbone, in the same slice, we see different methods becoming hot. So we see here, node remove child is very hot for the Backbone Speedometer test. Click again is still hot, but we also see insert before, append child, set timeout, element matches, event timestamp. And these didn't show up in the vanilla.js one because the Backbone app updates its UI by using the DOM APIs instead of using the inner HTML setter. So strategies that we would use for improving the vanilla.js benchmark performance and the ones we use for improving the Backbone ones might not be the same because they use our APIs differently. And then jQuery spends a lot of time parsing. Again, not the framework itself, it's a particular application that we're measuring, but we can see here actually a fair amount of stuff. So if we look at parser append child, we see that over the course of the test, we append 310,552 children. But those aren't all in the DOM at the same time. It's just we like to update the UI over and over again, and we make new nodes each time. And that's in response to 609 requests to parse HTML, which correspond to calls to set inner HTML. And then we can also see the contributions of other parts of the parser, like tree construction and tokenization. So with that information in mind, our strategy has been to dig in with more detailed tools like profilers, event tracing in Windows, instruments on Mac, pprof on Linux. And then we usually use the usual tricks that everyone does, profiling, benchmarking, micro-benchmarking, staring at disassembly, trying to change something, seeing if it helps. And so this is just a screenshot from pprof that looks particularly impressive. You remove a node, and there's like a little bit that's spent actually removing the node somewhere in there, and then the other 95% of the time was spent telling the rest of Blink that we removed a node. And then this work leads to performance wins. So this is a performance win landed by Aditya in event dispatching. So what you see here is a graph from Chrome Perf showing a Blink Perf micro benchmark for event dispatching. So here units are runs per second, so higher is better. And you see we landed a change which actually made a noticeable step up here, both on Android 1, which you see at the top, and Linux, which you see at the bottom. And because we track runtime call stats on Perf as well, we can see the same change reflected in the time spent dispatching events in more realistic web pages, like here the V8 Top 25 set. So here units are milliseconds, lower is better. And you can see the blue line, for instance, is CNN on Mac. And the time spent dispatching events, again, step down at the same time on a real web page. And so we see the results both in our micro benchmark and in our in our perf bots simulation of real world. So what are we going to be up to next with respect to Speedometer? Well, firstly, any contributions to improving Speedometer are welcome, especially from teams owning components that Speedometer does spend time in, both synchronously and asynchronously. We're going to be continuing to use measurement and profiling to improve the synchronous performance, and that hits a lot of the script bindings and DOM performance. We're going to compare in more detail to other implementations of the web platform to identify areas where better performance and score is known to be possible because we have an existence proof. We're going to break down contributions of both synchronous and asynchronous work to our Speedometer score. We're going to keep an eye out for regressions, and we're going to keep an eye out for Speedometer 2.0, which is going to be coming out soon and will give us plenty of new things to optimize. And with that, thank you very much. I'm happy to take questions. If you have questions afterwards, platformarchitecturedev@chromium.org.
So for the measurement of the asynchronous work, you mentioned that the benchmark uses set timeout, and I think that could, or that may or may not capture time spent in the compositor commit. Is that correct? And do you think that's something that kind of skews the results when we just look at the score compared to other browsers?
I mean, there's certainly, if you wanted a way to cheat at Speedometer, waiting until that timeout before you did things would be a way to hide performance from Speedometer. In practice, the synchronous work probably takes more than a frame time, so we should have a begin mainframe coming in, and I'm pretty sure that in the case of begin mainframe, we'll go all the way from style through to push to compositor to commit. Someone who knows differently can correct me on that. It's been a while since I touched the compositor. So I think that work is being included. I haven't gone through the effort of finding a way to plumb a trace event out from where Speedometer actually begins and ends measuring and seeing exactly what lands inside that. That would be interesting to look at.
Yeah, because it seems the trace measurements would actually be able to separate that work out, whereas just the raw score would not.
Yeah, the tricky bit is if you want to look at exactly what Speedometer is measuring, is finding a way to hook from Speedometer, the Speedometer runner, which is script, out to firing some sort of thing that you can actually see in tracing at the exact right time. It's not impossible to do. I'm just not aware of someone having done that.
Should be really easy just with performance.mark or measure. You can call that in JavaScript and it shows up in a trace.
Good to know.
I was going to add, though, that it's also pretty complicated. If you really want to say how much time are we using, that's a pretty If you want to include all of compositing and whatnot, that's a hard question to answer because first of all, it's not exposed to a web platform. Second of all, it's not even clear exactly what you mean, especially when Chrome has a bunch of things in it that in other browsers are part of the OS. So do you want to know until you've actually asked the GPU to swap, or do you want to know? Do you want to include the time you spend uploading the GL commands? Like there's it's not clear what the endpoint should be, and it's certainly I thought you were going to say this, Tim, because we've debated it with Web Working Group over and over again about what exactly we should expose to the web in terms of compositing time. We all have different implementations. So.
That's a fair criticism. At the moment, Speedometer measures on the main thread, and I don't think that's a terrible proxy. Because that's the time at which the user can't do anything else while interacting with the page. But it's certainly not a simple question. That's why we have teams dedicated to figuring out what we should and shouldn't measure.
So first of all, small comment on measuring the so-called asynchronous part of work. So it can probably be more reliably measured by just forcing it synchronously by forcing layout, by accessing layout-dependent properties.
That's an interesting thought. Firstly, not what the speedometer runner does. So for speedometer 1.0, that's...
I mean, for future versions, because currently you depend basically on compositor scheduler logic at scheduling the frame. So that kind of probably skews your measurements a bit.
I'm also not aware of a way to synchronously force either paint or compositor command.
Well, paint you cannot, but layout and style recalc.
Yeah.
So paint is like presumably rasterization, and compositing would happen asynchronously anyway, right?
Well, rasterization, yes, but the initial paint to a buffer, no. I used to work on the paint team, so I care.
Kind of a shameless plug on behalf of DevTools team, so you could actually measure time spent in bindings with DevTools profiler. It's off by default, but there is a check called show native functions, I believe. So basically, we've got a sampling JavaScript profiler, and with this setting on, it also samples names of the bindings. So basically, when it takes a sample, it also gets the top level, the name of top level callbacks. So you could get a lot of what you have as custom instrumentation just from the tools available to user. You won't get the execution counters though.
Okay, thank you.
I have a question around, so I help maintain APIs that are not part of Speedometer, like storage stuff like IndexedDB or cache storage or storage things. What advice do you have to us maintaining things not in Speedometer to either to have them covered by a benchmark that is modeling real world and not micro benchmarks, whether that's adding to Speedometer or creating our own. I mean, IndexedDB probably isn't the best for a to-do app, but would be great for like a spreadsheet or something with a little bit more data intensive. What advice do you have, or has anybody else tried to go down this route?
It's a good question. I don't have a good answer for you. It's basically, I think that that's an interesting thing to address. We certainly have micro benchmarks for some of that stuff landed in the Chromium tree. As far as including that in a real world benchmark, I would talk to some of the DevRel people like Adi Asmani, who might have more insight about what their thinking is about this sort of, including this sort of thing in these cross-browser real-world benchmarks. But I don't have anything specific to tell you that I know off the top of my head. Sorry.
Would that be something? Okay, I'll chat with them and maybe.
So certainly, if you find once having done that we're spending a lot of time in the bindings team is interested in fixing that. But as far as getting that stuff into those benchmarks, I don't have anything specific.
One thing to keep in mind here too is we can be gathering real world data via UMA, etc. We don't necessarily need to have benchmark coverage of, or real world benchmark coverage of every single feature.
There's a lot of behavior, like those of us that work on input, for example, we're never going to get good benchmark coverage because you got to model human behavior. And it's like, well, what time do people start scrolling after loading a page? And so like for scroll performance, for example, we kind of rely really heavily on the profiling based on the data we get from UMA. And regression benchmarks are really important for optimizing and being able to drill down. But in terms of covering everything, I think you're never going to be able to beat actually collecting data by UMA.
Still really want it for
So if you think the user story is super important, so you should chat with DevRel and create a benchmark, because for example, the service worker latency, so this is super important for next billion users, and PWA, it is clearly not covered by Speedometer, for example. So if you think your user story is super important for real world, so you should chat with DevRel and create a benchmark and optimize.
It's a small comment. One thing you can do is that if you know through UMAs or anything that some websites are using IndexedDB a lot or some of your storage, then make a list of these websites and then create a storage top 25 and put it on the waterfall. And that would serve as one of the benchmark, as the speaker mentioned, that this was showed like when they optimized speedometers actually showed on this list as well.
Yeah, the hard part with IndexedDB is that it's often run in the background as like a task that's run much later. But to that point, I did do this for docs offline load, and I just manually created a benchmark based on tracing of a docs offline load, which was work, but it revealed great stuff. But yeah, it's complicated because this stuff isn't just like running immediately. It's a interesting beast.
Else? All right. Well, thanks again for your attention.